class, so I'd rather just wait on that. But let's go ahead and get into section 3.4. We do have quite a bit of notes to take from this section. If you guys remember from Friday, which you probably don't, so let me just remember. Whenever I say that, I'm pretty much going to tell you exactly what I thought maybe you remembered. Section 3.4, having to do with concavity. Yes, if you ever don't get a handout, it's up here in your tray right here. There's one that we haven't passed out yet, so don't grab this one. That's not going to help, but any of the other older ones like the AP 1 and 2. We just started getting into what concavity is. Remember we checked our evens for section 3.3 on Friday as well, and it's taped if you guys need to access it. Say maybe you got caught up on 3.3, then go watch the video from Friday, check your evens, make sure that you're doing all right, etc. But then we got into 3.4, talking about concavity, saying, hey, there's the normal concavity, concave up and concave down, but there are also individual branches that still have the exact same concavity. And so we took a second to say, okay, you know what? Concave up, sometimes the function is decreasing, sometimes the function is increasing. Well, same. Concave down, same thing. The function could be increasing or decreasing. So increasing, decreasing does not relate to concave up and concave down. But then we said, like, hey, let's talk about the slopes. How are the slopes changing? And we figured out for any concave up portion of a graph, the slopes are increasing. And for any concave down portion of the graph, the slopes are decreasing. So we're like, okay. So if the slopes are doing the increasing or the decreasing, causing the concave up or the concave down, I think there's something that we could say about that. And we did. But did we write this down? That's the question. This is probably about where we left off. This is forever number 26, right?
Yes.
Okay. And I was like, hey, good thing we had the forever quiz on Friday, because then we didn't have to add this extra card, and there's going to be another card this section too. So at least, even though it might not have been the greatest timing in the world, you didn't have 2 extra cards that you had to study. So we can separate those. And maybe we'll have another forever quiz on just these 2 cards. And you're like, sweet, I should ace that one. Right? The concavity test. What does it take for a function to be concave up or concave down? And that's not necessarily the biggest question. Maybe the biggest question is, what does it take for the first derivative or the rate to increase, or the first derivative or the rate to decrease? But both of these questions are answered by, and both of these questions are answered by the sign of who? F double prime. The sign of F double prime. And remember, kiddos, whenever I have greater than 0 or less than 0, you can simplify if your brain doesn't like those inequalities. And F prime of X is positive. It works. They get it. Or for the next one, F double prime of X is negative. If that works better for your brain, put that instead of the inequalities. I don't care. And then the third one, if F double prime of X equals 0, then F prime is constant at that point, or maybe over that interval. And F has a possible inflection point. Now, as you guys are writing that, when we were doing hints for AP number 2, which reminder is now due on Wednesday instead of Tuesday, to let people do a poll work and have a little more time. And groups with poll workers in it. That sounds so sassy, huh? Aren't you guys simple? Anyway, so then coming back. When we were talking about the clues or the hints for AP number 2, didn't we talk about inflection points? Do you remember what they are? Inflection points. They're not maximums, they're not minimums. What are they? No, not a vertical asymptote. It could be a vertical tangent line. It doesn't have to be. It could be a horizontal tangent line. It could be just like a sloped positive or negative tangent line. Points of inflection. We'll get back to it. I was just seeing if any of you guys did remember, but we'll get back to what they are. We just started talking about concavity. Do you guys almost have this test written down? 5, 4, 3, 2? Okay. Oh my goodness. We should just start stressing. Wait, first of all, we said that we need to just look to the Lord and stress, right? And second of all, sometimes you just gotta start working and then hope and pray it'll work out somehow. So you're starting to write even though you don't want to. sometimes you figure out a place that makes you happy, like a coffee shop, and then you go just sit there for hours, and then even though stuff's hard, at least you're having coffee, or gumbo, or ice cream, or Denny's Grand Slam. I don't know what place is open late, you can do homework at. Has anybody done the Denny's thing? No. Just wait till college, then you can do the Denny's thing.
I went to Denny's on Friday night.
Nice.
Sean and I got really bored, so we visited a hundred from home every week. It's awesome.
Denny's is a good one. We keep on refilling coffee. Then I've rated there a few times until it goes away. But then I kind of fall asleep in the booth. And I go take a nap in the car and then I try again. Maybe it's not the best one. Maybe comfort food doesn't keep you awake. Anyway, come back. As you're writing, does this look completely
No.
I see discontinuity is number 1. I see, okay, number 2 is a little different, but there's a pitchfork. Number 3, sign chart. Oh my goodness. What is this like? Section 3, what were we testing? We didn't use this for mean value theorem. Mean value theorem was continuous differentiable and then F times C was F. What did we use? Discontinuities, critical numbers, and sign charts to analyze a function for. Increasing, decreasing. So analyzing for concavity, it's not really that much different than analyzing for increasing, decreasing, except instead of looking at the first derivative of a quantity, we're looking at, ready? Let me clarify with a highlighter to make things obvious. Concavity, we're looking at the second derivative. That's the only difference, guys. It's the only difference between section 3.3 and section 3.4. Section 3.3, we were looking, analyzing a function for whether or where he was increasing or decreasing. We were looking to the first derivative's pitchfork, but now we're looking for concavity, and we're looking to the second derivative's pitchfork. So what does that mean? Well, you got to find the second derivative. Okay. And after you find the second derivative, try to make them look like a nice fraction. And then after you make them look like a nice fraction, set the top equal to 0 and the bottom equal to 0. Huh. I think this sounds familiar. But these aren't called critical numbers. Do you guys see what the little pitchfork is called? Uh-oh. Who on earth is this? Great Expectations? Anybody? Sad day. Is it Miss Habersham? Crazy lady in the wedding dress? No one? You guys not? Pitiful. Anyway, just kidding. Love our English department, but sad. Okay, so solving for the second derivative function and find the pips. The possible inflection points. Oh! Pips. Possible inflection points. Now, does possible mean actual? No. Possible means maybe. But that's okay. We'll figure out what it takes to be an actual inflection point soon enough. Pips are the pitchfork of the second derivative. And then, looking down, number 3, sign chart. Use discontinuities of the original function. Hey, isn't that what we did for increasing, decreasing? Use number 1, and use number 2, and the pips. Oh, that's what we did for increasing, decreasing. So mark intervals on, or make intervals on a number line. Plug a test point into the who? Second derivative function. Remember, this is F double prime, concavity, everything F double prime. To check its sign, sketch the conclusion for the behavior of the original function below. And what I mean by that is for F, if F double prime, maybe I should do this. If F double prime is positive or negative, that means that F is concave up or concave down, depending on. And we could, if we needed to, which we usually don't because it takes a little extra time. If they ask for concavity, they're not really asking for this third step. But we could say that F prime is increasing or decreasing. That's how all 3 of them connect. And technically, if we were to do it in a super snazzy order, I suppose I would actually put this one third and this one second. Because the positive or negative of the second derivative tells us the increasing or decreasing of whose derivative he is, whose first derivative he is, which is f prime. And then that tells us f's concavity. But, but these are the two main pieces that we're going to be doing. Figuring out where f double prime is positive or negative. And as a result, being able to skip and say that f is concave up or concave down by the concavity test. By the concavity test. Not concavity. Ha ha ha. Oh, well, what is that reference? I'm still super surprised that no one's right there. We'll check in period 6. It's a good one to use on AP essays. All right. So let's keep going. Why is this a great example? Come on. He's a polynomial. He gets to use power rule, and he doesn't have any. What's number 1 say? Check for discontinuities. Does he have any? No. So step number 1. Now, hold on. Just because it's a Monday. That's fine. Can you remind me real quick, how do we know he doesn't have any discontinuities besides the fact he's a polynomial and he's smooth and doesn't have any weird breaks or jumps or holes or vertical asymptotes? No. He has no what? Square root. Good. What else doesn't he have? No denominator. What else doesn't he have? No logs and no trig. He's golden. Okay, discontinuities? None. You say domain all real numbers. Does that work? He's fine. Okay, number 2. All right, we just follow the steps. And number 2 says find the second derivative because concavity. This connects the double prime of whoever we're looking at. And we have f, so f double prime. So, before you can find f double prime, what do you have to do? Are we going to keep practicing our deriving skills? So I bring down the 4, it's like deriver's training. X cubed minus 12x squared. Don't go factoring, we have to go again, just leave it, right? We'll simplify the second one if we need to. You guys agree? Cool, f double prime, who is he? Minus? Okay, don't forget, in power rule, you have to decrease the power by 1. Simple mistake, and yet it happens all the time. Now, why am I going to go ahead and factor this puppy? Because I can, and aren't I to the step where I need to set equal to 0? Why am I not pitchforking? Because I don't have a bottom, I just have a top. Whether you're doing section 3.3 or section 3.4, section 3.3 you find the first derivative, set them equal to 0, factor and solve. Section 3.4 you find the first and then the second, factor set equal to 0 and solve. So what are my pips? Here, let's not do periods, it takes too long, right? Pips, possible inflection points, don't worry, we'll write them down soon enough. You guys already said it, say it a little bit louder. Positive 2/3, right? Step number 3 says, cool, take anything from the first one, I didn't have any discontinuities, okay, fine. And from the second one, okay, 0 and 2/3. And plug it in a sign chart. Sign chart, snazzy way of saying number line, right? However, why? Because sometimes these number lines are limited. Sometimes they only go to a certain number on the right, certain number on the left, and we cut it. Why is this one going forever? That's my domain, all real numbers. Have it go forever. This is like the x-axis. We're saying the possible x's. We throw in 0. We throw in 2/3. Wait, throw it in the number line. But then, when we're trying to analyze f for concavity, we have to figure out the signs of f double prime. So we're going to test stuff. Right, guys? Give me something. I'm not even going to say anything because there's no magical answer to this. There could be lots of different things. But give me something I should plug into who? The second derivative. To test the far left interval. What's the number? Sure. But couldn't you have done -5, -10, -2, negative, whatever your favorite number is, that's negative. But I agree, -1 is what I would have chosen. plug in something. To who? The second derivative. And I would plug it in the factored one, because who wants to really square it and multiply by 36? Not me. And all we need to figure out is the SIGN what? Sign. So, plugging in a negative, that's a negative, right? Plugging in a negative, negative 3 minus 2, that's a negative. A negative times a negative is a... All I'm doing is plugging in enough to get the sign, but I don't care about the number. I'm not graphing it, and even if I did, I wouldn't be graphing f double prime as a point on f. I'm going to keep on testing, then we'll go to plugging in the sign chart. What's something, anything? 1/2? Sure. Could have chosen 1/3, could have chosen 0.1, could have chosen 0.2, 0.3, 0.4, 0.5, not, 0.6 would work, but not 0.6666666. Plugging in 1/2, 12 times 1/2 is a positive. 3 times 1/2, that'd be 1.5, minus 2, that's a negative. So plug it in, a positive times a negative is a, just checking the sign. If you want, you could technically be plugging, I suppose, these into a calculator and getting a precise number, but we don't care about that. We just care about the sign that results. Give me something, anything, on a number line to the right of 2/3. 1 works, or 5, or 10, or 100, or 1,000,000, but 1's usually easy, and he's bigger. He's on this part of the number line. 1 times 12 is a positive. 3 minus 2 is a positive. What's a positive times a positive? So let's take these signs. Let's throw them in our sign chart. Positive on that interval, negative on that interval, positive on that interval. One test point tells me the entire interval. Now, if I had a little f prime here, don't write anything. If I had a little f prime here, I could say, yay, he's increasing, decreasing, increasing. Why? His derivative is positive, negative, positive. But we're making a jump, and we're saying, great, that's all well and good, but you know what that tells me about who? About f? That tells me that, since f double prime is positive, f is concave up of the cup. Maybe not the whole concave up, but I just kind of do a whole concave up to generalize. Maybe it's just one of the branches. Maybe it's the other branch. It's some sort of concave up piece. You could say CU if you don't even want to draw that. You could say CU. That way you're not drawing something that's kind of half wrong if it wasn't the whole concave up. Either way. But for sake of simplicity, I'm just going to do the little cup, and the little frown, and the little cup. Smile, frown, smile. 2 smiles and 1 frown. We'll say we're doing all right. So then how do we state where f is concave up? Intervals, just like we did before. And x intervals, just like we did before for increasing, decreasing. So where is, well, this part's concave up. On the number line, what x's are those? Everything to the left of 0. Negative infinity is where we would start then. All the way to who? Where do we end it? 0. And since the second derivative is 0 there, we have an open interval. Or starts being concave up at 2/3, and when is it going to end being concave up? Positive infinities going to the right. Concave down. Well, isn't it just in between? So we're just using that interval notation to tell us which x's on the number line this condition works for. Now, do you guys remember when we did increasing, decreasing sign charts? First, we learned increasing, decreasing, and how it happens, how it corresponds to signs. Now, remember, increasing, decreasing, that was f prime, not f double prime. But then, when the signs changed, didn't we learn that something important happens of an increasing, decreasing sign chart when signs change? And the function exists. If the function exists, and the sign of the first derivative changes from positive to negative, f changes from increasing to decreasing. What was something special that happened at that sign change? Relative maximum, the first derivative test. Or if the sign of the first derivative changed from negative to positive, so f changed from decreasing, to increasing, what's something special that happens at that sign change as long as f exists? Is there something special that happens when the signs change of f double prime? Well, let me really quickly show you a graph of f, okay? Let me show you a graph of f, and let's check our concavity and make sure it makes sense. From negative infinity to 0, here's 0, right? X equals 0. And then where's our 2/3? Okay, this one's a little bit harder, but 2/3 would be right about, there's 1/3, 2/3, because this is 1. Okay. What's the concavity before 0? Concave up. What's the concavity after 0 to 2/3? Down. What's the concavity from 2/3 to infinity? Up. So we have our concave up, concave down, concave up. What's so special about 0? He's a point in between which concavity changes. Is there a special name for a point in between which concavity changes? Inflection point. And then what's going on at 2/3? The graph is concave down before, and what is it after? Concave up. Guess who else is a plane inflection? 2/3. That's what it takes to be an actual inflection point, is for there to be an actual change in sign of the second derivative, signifying an actual change in concavity. And just like with relative extrema, you have to make sure those points exist to begin with for that to be true. Let's keep going. So, points of inflection. Points of inflection. So in ways, we're learning new things, but in ways the math really isn't changing all that much. Why is my board so tilted? I apologize. It must be annoying for you guys to look at every day. Points of inflection. Who are they? Points at which concavity changes. Points at which concavity changes. How do they occur? I'm just going to show graphically how do they occur, and then we'll write algebraically how do they occur. Sorry, you don't have to stick along. Graphically, how do they occur? We've kind of seen some of these that occur at a horizontal tangent line. It could occur at a vertical tangent line. So concave down before, concave up after, concave up before, concave down after. Or it could be something kind of like what you just saw. It doesn't really have a special derivative at all. He's just something that's, I don't know, a little bit negative, or he could be a little bit positive. Just a slanted tangent line. So the tangent lines don't find as points of inflection. Sometimes critical numbers are going to be points of inflection if they're not relative extrema, but sometimes you could have points of inflection where the tangent line isn't very special at all. It's just something random, like a negative or a positive. Which is why we don't look to the first derivative for inflection points. We look to the second derivative, because that's what tells us about concavity of f. So possible inflection points. You guys have already seen the quick abbreviation that I use just to make it fast. The pips, right? Possible inflection points, the pips. That's when f double prime, if he has a top, the zero's at the top, and if he has a bottom, the zero's at the bottom. But once again, like critical numbers, f has to exist at that point first. So it should look very familiar in the sense of critical numbers. F had to exist, and f prime was 0 or DNA. Those are for critical numbers. For pips, f has to exist, and f double prime equals 0 or DNA. Wait a minute, wasn't that one of the things on the Forever quiz on Friday? I think this one's kind of important too, maybe. And it is. But before we zoom out and put a rounded box at the other, there's one more down below. Possible to be a possible inflection point, to even have it be a chance, f double prime has to equal 0 or dne. And remember, the dne comes from the denominator equaling 0. And f has to exist to be an actual inflection point. First of all, it has to be a pip. F has to exist. F double prime has to be 0 or dne at that point. But then f double prime must change signs, which shows the concavity of f changes. That's the definition of an actual inflection point. I guess we could call that AIP, but that's just kind of weird and awkward and not so much fun. And if the AP is asking for an inflection point, they're not going to want you writing some little acronym. So we'll just keep it an inflection point. They won't say actual. That's for us to realize. An inflection point, not a possible, an actual inflection point. The sign has to change as well. I'm zooming out. I'm getting a rounded rectangle. Ah, where is he? There he is. Making him yellow. Boop. This is forever number 27? Thank you. Forever number 27. So we just saw it on a page before with this graph. I won't go back to it, but there were two actual inflection points. And the reason was, well, yeah, the graph showed it, but my little sign chart showed it too. There were sign changes of points that existed from the beginning in the function. Those are actual inflection points. This is a question every AP test ever has always had to find inflection points. So, whew, oh man. This looks like one of those ones in section 3.3. How come? Why is it intense? Do concavity. Well, okay. I have to do two things. What's the first thing we're going to have to do? Discontinuities, right? It's okay. I'm doing it with you. I'm feeling the pain, feeling the burn. Something like that. Question. Discontinuities, what do we do? Put the denominator equal to 0. Ah, stink. Seriously? Mm-hmm. So x squared minus x plus 1 squared equals 0. Now some of you have figured out this trick and some of you haven't. Do I really need to worry about the squared? No. So when I square root both sides, guys, what's the square root of 0? 0. So it's not going to matter, right? Just look on the inside. Look in those parentheses. Ah, and I have to set that equal to 0. Well, stink. How do we set that equal to 0? This is a really mean one. I chose a really mean one for classwork. We practice hard so the games are easier, right? Okay. Faster? It doesn't work. Okay. We could complete the square, or we could do x equals negative b plus 2 minus square root b squared minus 4ac all over 2a. Ah, it's going to be disgusting. More than disgusting. It's going to be what? What's 1 minus 4? Negative 3. Oh, it's imaginary? What does that mean? Now, some of you get confused here, but some of you start like throwing a little party in your head because if it's imaginary, are there any discontinuities? No, they're imaginary. Imaginary discontinuities won't be problems for us. So therefore, I can say discontinuities? None. Sweet, what does that mean? Oh, the domain is all real numbers. We don't mind imaginary discontinuities. That means we don't have any to worry about. Good. It's like imaginary worries we can just ignore. Number 2, even though we're not so good at it. Number 2. All right. The discontinuity problem got solved. There aren't any. Domains all real numbers. Number 2, okay. Steps. Nothing new got added to point of inflection. We're still doing concavity things. Find the second derivative, but you can't do that until you do what? Find the first derivative. You have to be kidding. I know. I'm feeling the burn. I'm doing it too. How are we going to have to find this derivative? I have to do quotient rule, right? Flip the table. It's okay. We're persevering, yeah? Nice. It's okay. Every time we're taking a derivative, we're getting better at it. Don't make mistakes. That's where we can ace this. We need our first derivative to find our second derivative. Okay. Bottom v top. Come on. X squared minus x plus 1. V top. What's the derivative of x minus 2? Minus. Top v bottom. Derivative of the bottom. Okay, come on. Come on. Why 2? What are you doing? U squared. You're bringing down the 2. Chain rule, right? Keep the inside. It's to the power of 1 times U prime. And who's U prime? Got it. All over. When you square, what do you get? Got it. Okay, now hold on. I'm showing you some harder ones in this section, because in section 3.3 I didn't show you enough hard ones, and you guys all freaked out by taking derivatives. I know. Derivatives can be scary. I get it. I totally get it. How do we simplify this mess? Some of you would be like, forget it. But what you're seeing is that you have to FOIL everything, and you don't. All you have to do is look. And not all you have to do. Not saying it's easy. But look, there's a big old minus. Grouping these into 2 pieces. Bottom v top minus top v bottom. Is there anything shared? What do you do with shared stuff? Pull it out. Pull that shared stuff out, right? Any common factors? So you can pull out an x squared minus x plus 1. Who do we have left? First piece. We have one of them left, right? X squared minus x plus 1 minus. Put a big old parenthesis because there's going to be a lot of minuses. But we got rid of one of them. Okay, minus. We got rid of this whole piece, right? That's gone. What's left? Well, we have a 2. Okay, let me throw that 2 in front. Is that okay? There we go. We have a 2. I'm just throwing that 2 in front. We already got rid of him. We have an x minus 2 and a 2x minus 1. Now, I'm not saying this is gorgeous, but it's easier than it was a second ago. And what can I do with that big old x squared minus x plus 1 on top? Whew. All right. Whittling it down. Right? We're whittling it down. Now I'm going to go ahead and, sound like rewriting stuff over and over and over, because I know you guys don't either. I'm going to go ahead and FOIL this little guy right here. Let's FOIL him. Need that 2 in front, so put a little parenthesis. And I have a 2x squared minus 1x minus 4x, which will be minus 5x, plus 2. Okay. So we FOILed him. Now we can ignore that little thing. You have to distribute that little negative 2, but it's okay. Slow and steady wins the race. Remember, you get some coffee or something that's comforting as you're doing this. Nice thing about math is sometimes if you're just doing stuff like derivatives, you can be listening to music or maybe even watching a show, as long as you're being very careful. Can't really do that when you're writing an essay, or you shouldn't be, my ones that try. Negative 4x squared plus 10x minus 4. Now I can say 1x squared minus 4x squared is negative 3x squared. And negative x plus 10x is plus 9x. 1 minus 4 is negative 3. Okay, what do you notice about that top, guys? Yeah, I see a negative 3 that can come out, right? All over. Whew. Who's that? Ooh. Who's that, guys? That's the first derivative. No way! Okay, pause. Pause. What would you have to do now? Find the second derivative. Hold on. Class is almost done, so let me just go ahead and share a strategy with you. Okay, ready? Let me share a strategy with you. Maybe I should have shared it in section 3.3, but we were trying so hard to get that thing off the ground and we were just going for it. So let me share it in 3.4. Those of you that have felt the pain in 3.3, what pain? The driving pain, right? Okay, because everything else, okay, hopefully everything else isn't too bad, but sometimes the derivatives just discourage you. It is what it is. In homework 3.4, maybe it might be kind of hard to tackle right now in 3.4, to tackle the entire homework. Since actually there's one more forever card we need to cover, it's really just the end of homework. Technically, with what you've seen today, you could pretty much tackle the first half, if not 2/3 of homework. But maybe you're like, you know what? Let's be honest. I get discouraged when the derivatives get rough. Okay? How many of you guys would say, I get discouraged when derivatives get rough? I get discouraged when derivatives, like that's rough. I agree. I'm going to go ahead and finish this one and have that double line just waiting for you guys tomorrow so we can just look at it and do a sign chart with it. But hold on. If you get discouraged when the derivatives get rough, here's something that we did last year. I think it helped. The kids went ahead and looked in homework, and before tackling the entire homework assignment, they actually had a little in-between homework. Wait, listen. And they called it the homework whatever in this one, homework number 20, the section 3.4 reference guide. And what they did, before tackling all the homework and all the concept-y things in the graph and everything else, is they figured out the sections where they were going to have to do concavity and points of inflection. And they said, oh no, we're going to have to find second derivatives of all of those. And they took those numbers, and before they even started their homework, they're like, fine, I'm going to do all my derivatives first, and then feel really good about myself and not have to worry about them later. If you're one of those ones that get really discouraged about derivatives, you can tell in your homework, it's like the ones that have just equations and they just have concavity or points of inflection. You're going to have to find second derivatives of the ones that I've given you. I've lessened the problems in this homework. So make yourself a little reference guide in your spiral. Just call it homework number 20 reference guide. Just go find first, second derivatives tonight. Sound good?